Yeah, try to keep this introduction short as well, so we get more to the sort of hands-on part. But a little bit of information adding on top of what Joachim already said earlier. There's, with IoT devices, particularly if you go from sort of like the demo setup to something that is a little bit more sort of production ready, also industrial space and consumer space, you want to have some way to manage the devices. And this is what lightweight M2M is about. And this management comes into multiple different sort of functions. One of those functions is the actual configuration and retrieving the values, and we are going to see that in the demos later on or in the hands-on examples. There are also security functions that you want to do with these devices, such as firmware updates. We are not going to do that today, or the distribution of key, and I will show that in the case of Lesharmin and sort of on how you could do that. So there are a couple of basic features that you definitely want for most of those devices, and lightweight M2M as a protocol provides you those basic building blocks. Joachim walked you through that diagram already, this sort of client server architecture, and what we are going to see later on in the demo is the client, lightweight M2M client, sitting on one of those small boards. I will hand out the boards later on, but just to give you an idea, so we have, for our demonstration purposes, we use this Freescale developer board, and it obviously comes with a sort of application processor there that we are going to program. But then it has, as it is typical for these developer boards, it has lots of breakout connectors, so you can connect all sorts of sensors and actuators. We are not going to do that because often that requires a little bit of, first of all, the extra hardware, which I have a few samples with me to show you how that works, but we'll focus more on the onboard sensors, which this device also comes with. What is interesting to note about this lightweight M2M, as the name already indicates, there's this lightweight nature of the protocol, and this is sort of comes from the design, but also the reuse of certain technologies that are very focused on smaller devices in terms of memory needs, sort of flash memory, RAM, and also over-the-air transmission. So here we use Ethernet because it's easier to work with in sort of this almost lab setup. But it could as well be a Bluetooth Smart. It could be some other very constrained radio technology. Sean, could you click on the slide? Yep. There are a couple of operations that happen between the client and the server. And the ones that we are going to see most is, or at the beginning, is we start with registration. So you will see that there's initially when the device boots, or you reset the device and it loads its code, it starts with a registration procedure to make itself available to the backend infrastructure, to the cloud server in this specific case. And then as we then use sort of an API to access the values, there will be reads, in our case, be executed on the value on the board to retrieve the latest sensor values. But we can, however, also use sort of a publish-subscribe paradigm, which is the last diagram here, which says this observe, sort of subscribing to a value and then receiving notifications whenever the value changes. All this is described, of course, in great detail at the OMA lightweight M2M specification, and you have the slides available for download in case you want to use them, I guess, even in PowerPoint format, do we?
Yes.
Cool.
If they're not available right now,
about, yeah, so you can use them, click on the links. There's also an issue tracker I would like to make you aware of, so in case you play around with this stuff, and you can actually then report some bugs. And there's a wiki page that Joachim mentioned already with lots of more information. There's also a popular open source server library, Leshan, that you could make use of, and I'm going to show that a little later. One important point that I want to already sort of mention now, which we're also going to see in more detail later on, is this object model. So how do you address specific sort of data on the device? So if you have this device, it actually has multiple different interesting sort of resources there. It has several buttons. It has an LED, which you could configure. And it also has an accelerometer and a magnetometer. And there could be many other sensors attached to it. So how do you actually address those in a meaningful way? And this is where the object model comes in. So in this case, and of course there's also access control lists associated with it. So how this works is as follows. So in the lightweight M2M specification defines a somewhat simple object model by saying that there's this three tuple consisting of an object ID, an object instance, and a resource ID. So let me show you what that means. Here's some examples on already defined objects, things that people in the industry considered useful for use with those devices. So for example, the device as a specific object name, which of course itself has a couple of different attributes which are called resources. So how to describe this specific device, and we are going to see how this device description looks like in later on. Here I have an example from IPSO in case of a temperature sensor. So there's no temperature sensor on this device, but I think you get the idea. So there's this object defined. It has a specific number. So the object and resources are defined by numbers. So you see, can I use it? Okay, it has by that. Yeah, cool. So here, for example, this has an ID, and this means, okay, this is a temperature sensor, a definition for a temperature sensor. And it has a couple of attributes. And in this specific case, it has three attributes, namely with those numbers. The first one is, and probably the most interesting one, is the one with the sensor value itself. So like, what's the temperature value? And you can read that value. For this object, it only has a single instance. It describes the data type and the unit. So if you receive the data, you actually know what the semantic of that value is. There's a little bit of metadata defined here as well as two additional attributes: minimum measured value, maximum measured value. And whether you use that object as with only one attribute or with all three is up to your application and your needs. So that depends a little bit. But you can pick and choose from different values. And here's an example of values or different objects. And I'm not showing the different attributes, the resources, because that would be a little bit too much. But there's behind this link, there's the pointer to the registry where you can see all of the standardized objects and their resources. So a lot of stuff. And so how are you supposed to use that altogether? So for example, if you have a device like a fridge or here an HVAC as well, you can take these different objects, and then in red you see the resources. You combine them to describe, for example, a fridge. And that's something that you want to sort of expose to your application. How many of those objects are used? really depends on what your application example needs and how detailed that description has to be and what you can control and what you can't. So I think that's from an overview point of view, I think that's enough about lightweight M2M. We see more about these objects and how to set values and so on later on in the examples. Okay, perfect. Turn this off. Joachim, who's next? Now it works. Cool. Okay. So we now get to the part where we do a little bit of hands-on. When we worked on, so what you will, at the end, I hope what you have there will be, you will be able to configure the device that you create some, you use the tools to create a firmware image and load the firmware image on the device, and then the firmware image will contain a lightweight M2M client that connects to a cloud-based service. That's what we hopefully will have at the end if everything works. We can use different tools to get there. So everyone has different preferences on what they want to use to develop software. I will primarily show the use of the command line tools, which are also linked on the workshop page. So you had a few instructions on how you could use those tools and download them. You can also download them then here now if you want. For those guys who can't download anything for whatever reason, there is also a web-based version of it. Some people like to edit code in a web browser. Okay. Some others, again, which I will also show, they like more professional IDE development environment, and you're free to use whatever you want. It doesn't really matter at the end of the day, but there are obviously differences in appearance and the debugging capabilities. But before I get there, I wanted to tell you a little bit about also the hardware and how we got there where we are today. And I wanted to, instead of introducing this usual IoT stuff and all these great predictions about how many devices we will have around, I wanted to show you a few projects that we are doing. And I thought, for example, this one is quite good and appropriate for the place we're in. The BBC has this project called MicroBit, where they want to give a small little computer to every 12-year-old child in the UK so that they can play around with it. And this is how it's supposed to look like: LEDs, buttons, and there's a processor there. It's an ARM-based processor, and I think it's a Nordic semiconductor chip. And I'm actually going to pass around the chip because I have a few of those with me. And so you can see how that looks like, because it's obviously fairly small, needless to say. So it's a Cortex M0, and I will explain you in a second what that means, M0 plus. And this device runs very similar software than this reference architecture. Of course, this one, the difference to this one is this is a smart city reference architecture that we have been. That's interesting. Why? Could you remove the bar over here? Good. So this one is another sort of design. So all of these designs that I'm showing, I have 3 examples here. You can download the code as well as the designs and sort of like, when appropriate, sort of the hardware reference files. Here we did a smart city reference architecture, and you're using the same pieces, but you're using different radio technology. In this specific case, you use a sub-gigahertz IEEE 802.15.4 radio. Different radio technology. Different radio than the BBC Micro, which uses Bluetooth Smart, which is very convenient for kids when they have modern mobile phones. In a smart city environment, you want a radio that you can use for meshing, for mesh technologies. So not the street lights, individual street lights are not connected individually to the internet, but they are connected with each other, which then go to a gateway and then to the internet, as this diagram is showing you. So if you go to the MBED websites, you see those details. Another reference design that we looked into to decide about what functionality do we need is a reference design for a wearable, a smartwatch. And also, you can also download this. This one runs on a similar processor and has an 8-week battery lifetime. Use the same software. Of course, it uses some additional sensors. For example, it has a fingerprint sensor, it has a GPS sensor, and so on. It's GPS receiver. So obviously, different applications need different sensors. But beyond that, sort of the operating system and the protocol stack is very similar. So what we want to get to is we want to bring IoT to scale, and not just sort of like for prototyping effort. Even though we do sort of prototyping things here, you can then go from that level to something that is product quality with the same tools, with the same technology, with the same stack. So you don't need to sort of like you don't develop the prototypes with one set of tools and in development environment, et cetera, and then when you want to develop a product, it would be completely different. That's not the idea. So it's the same stuff. And time to market matters in the productivity of the developer itself, security and connectivity, and also the diversity. And you see the diversity also with the number of hardware modules that are available. So you write that so we used today the NXP or the Freescale K64F, but you can then as well take a different board next time. And for example, I took one with me that ST Microelectronics kindly offered us. Is this? It's called STM32F7. It's a high performance board. It has a huge display, this development board, so you can open it and pass it around. It obviously has far more capabilities, and it's much faster and has more memory and everything else. It also has an Ethernet port built in the demo board, and so you could actually take the code that we develop or we use today, and then recompile it for use with this device. Without having to sort of like totally throw everything away. When we talk about connectivity, we talk about a fairly complicated protocol stack because after all, you know, the IE in the IoT, like we're talking about internet. So we talk about internet to the devices. That means a lot of different things. Not just the radios, the radio technologies that I mentioned before, but also like the IPv4, IPv6. Here we use IPv4 in this setup because that's what we got. UDP, the transport protocol, TCP. We use the security, and I have a separate slide on this because I believe that's very important. We use CoAP, as mentioned before, because it's part of lightweight M2M, and all the REST APIs. So we have to fit this whole protocol stack on these tiny little microcontrollers that I just passed around. Oops. This, I don't, can you, is it? For some reason, does it work now? Okay, cool. So if you drill in a little bit on the security side, there are at least 3 different components to look into. One is the device security, and we are a little bit cheating in the demo here because, as you will see later, we are sort of mimicking the manufacturing process by simply copying the keys manually. So obviously, in a real-world scenario, you would have manufacturer-provided keys, different keys for each device. But here every one of you just copies the key himself, and everyone will have a different key for the device. There's the lifecycle security, which OMA Lightweight M2M provides with firmware updates and all these sort of things. And there's the communication security, which Lightweight M2M also relies on, which uses DTLS and TLS, sort of the regular transport layer security suite And that's where lots of the code comes from, because this is hardcore crypto. When we talk about IoT devices, what is a differentiating factor between the different hardware components that we use is we have often limitations in terms of memory, RAM, flash size, processor capability, speed, particularly. There's maybe no user in front of the device. And we also care about energy efficiency for many of the deployments. There may also be constraints on the network side. People talk about low power, wide area networks. We talk about Bluetooth, low energy, and so on and so on. There's a whole document that talks about this, which I reference here below. In context of ARM-based devices, so the previous Arduino that was shown, that was not an ARM-based device. It has the bigger processor that you've seen, which runs Linux. Is a MIPS. It's still a RISC-based design, so reduced instruction set, which typically means smaller number of instructions and more registers. The ARM processors are also fall into that category, and the ones that we are looking into here are so-called the Cortex-M class devices. They can easily, sort of like from a developer experience and from a product point of view, there's also another category that you may be more familiar with. This is the A-class device, the application processors, which you run in your mobile phone, tablet, and your Raspberry Pi, BeagleBone Black, and these sort of devices. And that's a different class of devices. It's a different architecture. It runs regular Linux or Windows 10 for IoT or whatever. So more sophisticated operating systems, and the development experience would be very different. But also all the requirements, the hardware requirements, and the cost will be very different. Also the energy efficiency is also very different. So you can measure the energy efficiency or the energy consumption of a Raspberry Pi compared to one of those devices, and you will see obviously a huge difference. There are different, I won't go into details of the different processors, but just to give you an idea what boards you have in front of you. The K64F is a Cortex-M4. It's actually a very capable processor. It's the one over here. It's often, because of its capability for digital signal processing and this single instruction multiple data with the floating point unit, it's often used in sort of sensor fusion applications, audio processing, and these type of things. For the chip that I passed around, the Cortex-M0 Plus, that would be low power, small instruction set, no floating point unit, and in this case, this specific one, it has Bluetooth Smart radio incorporated. Bluetooth Low Energy. Yeah. And the other board from ST Microelectronics that I passed around, just open the board and have a look at it. There's lots of stuff on it. This one is the latest one of this series. It's a Cortex-M7. It's a very powerful processor. It is the first one in this series that offers a cache. All the other ones don't have a cache. And what they also are differentiated from the Raspberry Pi based deployment is the memory is actually on chip. So in the same package, you have the flash and the ROM is in there. So there's no separate, for example, DDR RAM. But there's also no concept of virtual memory. Like there's no memory management unit. That's why you can't run Linux on those type of devices. You may not even want to, because of like the Linux would be like, we're talking about megabytes of code here. But in this specific case, we are not. So here I have a few examples. There's a small one, Cortex-M3 with 120 megahertz. And here you see, like, this is a pretty oversized chip for many of the IoT deployments. But I had chosen them, this one for a good reason, not only because it has 512 kilobyte of flash, it has a lot of features, also hardware-based random number generation, and you see the prices there from last year. It's quite expensive compared to for small volumes. So if you buy large volumes, the prices would be significantly different. So you see, this is a company funnel. If you buy more than 2,000, then for an IoT deployment, like if you have a smart city deployment or something else, 2,000 chips is nothing, or for light bulbs or so. And so for higher volumes, obviously, if you buy 1 million of those, the price would be very different. But if you look at this one and compare it with the next one, oops, you see something interesting here, and that's why I put those there. Those two. So you see this is, why do I have a disconnect between what I see on my screen and what is shown on the display?
It will be a little bit delayed.
Oh, a little bit. So the stuff that you don't yet see, it's a much faster processor and has more flash, has more RAM, but it's much cheaper. And it's totally counterintuitive. You would think, like, how is that possible? And the reason is some chips are, because of manufacturing volumes, are more popular. And so people buy it more, the prices drop, the factory, once you have a setup cost for a factory, and so you may actually get a very good chip, very performant chip for a very low price. So you see that. And that's what I was trying to get across here. The chips that I passed around are obviously much smaller, but even from a price-wise, it's very different. Still, as you can see on the chart, on the diagram, it has lots of features. It implements even a very basic chip nowadays comes with lots of features, debugging capabilities, all sorts of different protocols, all sorts of different timers, real-time clock encryption, hardware-based encryption capabilities, etc., etc. So there's just because you have some of those features doesn't mean that you have to spend a lot of money. Also worth pointing out, and I often see that confusion when I talk to people and give them the boards, is there's the belief that the price of the board has something to do with the price of the product, but of course it's completely unrelated. This is a development board, and so I showed you one development board, and I want to pass you around a few other development boards that have different capabilities, different manufacturer, are supposed to illustrate something very different. And of course, the boards can be, if they are larger, like this one. This is a full-fledged development board that comes with a separate debugger and so on that our colleagues from Kyle use. Those boards are more expensive, but in a real product, you're not going to use a development board. And the price of the chip is actually not necessarily the dominating factor in the cost of the overall product. So there's a nice webinar recorded that you can click on the link that explains you some of those relationships. You have the cost of all the bill of material, including the packaging. And you may find that actually the foil that you use to wrap your final product may actually be more expensive than the chip, or 10 times more expensive than the chip. You need to think about long-term cost, energy efficiency, what the costs are if you actually get an engineer, field engineer out to the product to do the software update. Also the cost of development. If you have something that is highly optimized for some very special architecture, it costs you a lot of money. You need engineering manpower and to actually do that. Getting to the demo that we work with. So we, starting from the left-hand side, so we work with the board that has this ARM-based chip, Cortex-M chip that I explained. It runs an operating system that we develop and give away for free. It can be downloaded, it's open source. This device will then connect to the cloud infrastructure that we also provide, which we call MBED device connector. And then that is just a pass-through device, if you will. There's in a real service, the company who offers the product and the web service, they need to think about what's the value add. So if you have, for example, variables, the value add is with a sports watch is it tells you like how much you ran, it visualizes it nicely, it maybe shows you on a map on where you ran, on how much training you did, and how much training you should be doing, and how good you are, and who knows what. And that's what a value is, and so there may be big data analytics and all sorts of things involved. And we have sort of partnerships with other companies like IBM, with their Bluemix and other companies who provide that type of expertise for specific sectors to analyze on, like, basically take the raw sensor data and then do something meaningful with it. So if you have, for example, in an industrial environment, you have a steel factory, you have the sensor readings, just temperature readings, but the whole process is very complicated. You need to know, you need to understand how steel is manufactured to actually make sure that the temperature range stays in specific values to produce an optimal product. The connector, this cloud-based service, is located at this. If you have had a chance to look at the instructions that we passed around beforehand, that's what it said. So we are going to build the code for the device on the laptop locally for most of you. Connect it to the device, use that as a way to get the keys, and also to do a little bit of debugging to see what's going on. Just there's a API included in here to allow cloud-based services to access those the sensor values. That's what we do. This MBED connector for developers, that's for free. If you, of course, have millions of devices, then the story is a little bit different because we need to operate the server infrastructure. What is specifically on the code that we are going to look through is you will see a few things. First of all, you will notice that this is a C++ API. So it's something. Many of the embedded devices and IoT devices are developed in C. So that's why it's no different here. The benefit of doing that is you can reuse a lot of example code. So if you have sensors available, and some of the companies manufacturing the sensors, they actually provide you the example code and the libraries along with it. Very convenient. And it comes with TLS automatically, so we won't actually need to do anything. The default is transport layer security enabled. So you will actually have to figure out on how to disable the transport layer security. Yeah, and then there's a lot of stuff under the hood, which we won't look at, but of course feel free to look at the operating system if you care about these type of low-level details. It's written mostly in C. There for performance optimizations, there are some assembly files as well, for example, for some of the crypto. Good. I mentioned here that the importance of security. We use a library called MBED DLS, which is an acquisition of an open source library called Polar SSL. It's an embedded DLS stack that comes. You can use that also for free. The code is available for download. Has always been. Also with Polar, and it implements all the recommendations that the specification makes. You can also use it for other purposes if you want. And this is and shouldn't be underestimated, because the size of the code for the crypto often far exceeds the rest of the code. So it's as a developer, you better not want to write that code yourself, because that would be very time consuming and requires a lot of expertise. Good. So here are some of the links, and you should have also seen those links on the workshop page. So just for your reference, here's the board. So what the first thing we are going to do is plug in. So this is the Ethernet connector. Plug in the USB cable into this board. this is the one that we also use for connecting the debugger.
And notice the port itself is not polar. You have to be quite careful which way you plug
Yes.
in the
Yeah.
cable.
Yeah. And there's a second one. So if you plug it in here, you also power the device, but you're not using the debugger. This is the chip that I was talking about, the Cortex-M0. It runs at 120 megahertz. This is a very this is a device that is really useful for development because you will not have any memory problems. Like for Linux, this may be nothing size-wise, but for an IoT device, this is massive. So so an example, I didn't select features or deselect features. I just dumped everything in there, and it's like nothing. Also RAM-wise, like we could do all sorts of things with it. There's lots of different boards supported. So depending on what you want to do in your project, you may need a different board. So in this case, obviously, I selected this board because first it was available, second it had Ethernet, and which is convenient here. But if you want to use, let's say, some Bluetooth or some cellular radio, you can add extension shields, or you can get other boards and so on. So have a look at those links. There are two operating systems that we have developed. One is what we call Classic, and the other one is the new version. We're trying to harmonize them as we go forward, but I will show you how to develop with both of them. It doesn't matter that much for our purpose. In fact, I should include a link that points you to the Linux-based version of the same code, of the lightweight M2M code, so you can actually run it on a Raspberry Pi. But I didn't take a Raspberry Pi with me, so. But if you have a Raspberry Pi at home, you can still do the same stuff, but you will be working on A-class, Cortex A-class processor, not M-class. Different development experience. Okay, good. So did you successfully plug in? And what should happen is, and that's the nice thing with these MBED-enabled boards, is that the device should show up as a USB stick, essentially. So if that worked, that's good. That allows you to drag and drop the firmware onto the device in many others. So if you've been developing with embedded devices previously, you may know the hassle of connecting a separate independent debugger to the device and figuring out what the memory ranges are and where to copy the firmware and all these sorts of settings. Nothing of that is necessary here. This is sort of the easier development experience. There's a separate chip on it that allows sophisticated debugging. Good. I did that already. I connected my device. And as you see, well, or maybe see, so there's a separate, it just shows up as a device, as a USB device. And what we are going to do first is to make sure that we get something working. So the description of how to get the lightweight M2M is not the most basic example on Earth. You can also, if you want, Joachim, you can also take a board and
Yeah.
Oh, you have it. Okay, cool. No, this is actually the wrong link.
Do you need to sign up first?
Right. You need to sign up to the Mbed connector, because otherwise you need to get your keys for your board and not my keys, right? Let me see where my so this is so there are different. I copied this in here as well. So this is the example that we are going to use. There's a GitHub from this GitHub repository. So the code is in GitHub. For our new version, we used a different repository, MicroBit, for MBED OS, for the MBED Classic. but now we use GitHub. And so if I go to that website, you see the code, but you also see the description. And so this is the part, you need to create an account, and then we use a client on the desktop. We use a development environment to build the program. So, and of course, the software will depend a little bit on what operating system you run. Okay. Did you guys set up this already? You did. Okay, cool.
Just sign up.
Okay, awesome. So give me a sign when you guys are ready, or how far you are. Friedhelm, did you install the stuff already? No.
I have the Jota, but now I'm getting the account.
Okay. So you run the Jota in the Mac OS?
Yeah.
Okay. David, are you following along as well? I will run around a little bit to see how you guys are doing. What we try to do here is we just create the development environment. We need the code of the program and the operating system. And there's a little bit of development environment. So for example, so I can show you what I use. I run Windows on my work PC. And then but I prefer to do everything in Linux. So I'm actually running Ubuntu in a virtual machine, and I'm doing everything there, use Git and all the tools there. So Jota is a wrapper around CMake, and it also uses a component management system that is similar to NPM. And yeah, and then we use a serial monitor to get the debug messages. So the plus of using this sort of simple way of talking to the device using an USB sort of stick, USB flash drive, is just that we just drag and drop the firmware. For debugging, we use a serial monitor. So for example, I use in an app, there are probably 10 different ones around. So I use one in Windows that is called Teraterm. So I'm actually doing the debugging in Windows. You could also do it in Linux if you want. It's personal preference. Let me increase the font size a little bit. Okay. So I also, just to give you, while you are clicking around, just to give a different sort of view of the same development experience is, here I use an IDE from Kyle. I'm using the same code, but I'm just using this graphical editor, which provides me, so as some people at least, more convenience when they develop programs and also when building programs and debugging programs. You can download, there's also a free version of Kyle available that you can download. Of course, there are all sorts of other IDEs that you could use. The details here don't matter. There are lots of files. We won't go through those in this editor. But
how do you spell that, Kyle?
Kyle is spelled like, yeah.
K-E-I-L.
Yeah.
Oh,
Yeah, it's no, it's a German company that developed the IDE. Actually, they develop also operating systems, but their primary focus is on developing IDEs and the protocol stacks along with it. And ARM bought it up probably about 10 years ago or so. But there are all sorts of other. So it depends on, everyone has a different preference when it comes to the IDE. Like some people like Eclipse and some others like Visual Studio. I know people who use Visual Studio to write the code and then to do generate the code for these ARM devices, ARM-based devices. I'm actually using Visual Studio myself as well, but for more complicated protocols. And then once the things work, then I switch to a different editor, because then the development experience with embedded devices is more complicated because, as we previously heard, you have to generate code that doesn't run on this platform natively. So the tools that you download, sort of the compiler produces, and then the linker produces a binary that wouldn't run on the machine locally. So that's why it's often easier. For example, if I develop, I'm working on a new version of transport layer security, and so I can run the client and the server locally on my machine. I don't need to have a device connected. I don't need to sort of mess around with the complicated debugging settings. Just embedded development is more complicated. Like smartphone app development is also more complicated, right? Because you have to deal with the separate device. Okay, but here you can use all sorts of different IDEs. When in many of the smartphone development environments, you can only use one. Good. Talked about that. So what's the situation? Are we good?
You signed up.
You signed up, and did you successfully install IoT?
No, but I think we may have an issue with that because I don't think we can install it.
You can't install any programs on your machine? You can delete it afterwards again. It doesn't matter.
Yeah, but we can give it a try.
You could try it to see whether it works. So yep. Let me show you.
Yeah, I have as well.
Where's it now? Let me quickly. So here's the. So if you search for GitHub and MBED client quick start, which is the link that you should also see on the workshop webpage, you see a step-by-step version. And there's also a link to IoT, and this is the build program, and that there's some software, and the description obviously varies on how to install it depending on which operating system you install it on.